So we're going to be talking about the radiation of a spherical black body, perfect black body, and sort of the energy radiated outward per unit surface area of this black body we'll be calling J1, and the temperature of the black body we'll be calling J2, or T1, sorry. All right, now, I'm not going to draw this to scale, but suppose that close to this, to the surface of this here black body, we put a thin spherical shield, which is also a perfect black body. So we're just kind of shielding this inner black body from the outside world, and what we want to do is find out how much energy escapes out to infinity. Okay, so so energy, escaping per unit area, we'll call J2. All right, and we also want to know what is the temperature of the heat shield that we're putting around here. Okay, so in thermodynamic equilibrium, basically the energy that's coming in to this heat shield has to be equal to the energy that's going out. Otherwise, the heat shield would either be cooling down or warming up. Right, so assuming it starts cold, it's just going to warm up till it reaches this sort of this radiative balance where it's radiating as much energy out as it's getting, it's intercepting all of J1. So it gets J1, it needs to emit J1 to stay at the same temperature. All right, now the key to this is that this very thin heat shield is going to be emitting energy equally in both directions. So half of its energy will go out to infinity, and the other half is going to come back towards the inside black body. All right, so basically, again, here's the energy irradiated away, and here's the energy coming in. So these two have to balance for the T2 to remain constant. So J1 equals J2 going back in plus J2 coming out. So J2 is, it's also equal to, right? This is the only one leaving, so J2 is the only one that reaches infinity as well. All right. All right, so we know that the energy flux, I guess, reaching infinity is actually only 1/2 of that leaving the inside black body. So say this is a star or something like that. That's a good approximation for a star in most cases, I'm guessing. And you surround it with a thin, layer of dust or something. All right, so it just means, we can keep on adding these shields on and on and on, but each one, once it reaches equilibrium, it will only output 1/2 of the energy that it receives. The other half goes back inwards. So you could do a much more complicated, example where you have J3, J4, right, and they all kind of have this balance going on. And then I guess you have to consider energy J3 coming from this one coming back to J2, and so there's an additional term up here as well. There would be a J1 plus J3 coming into this shell, and then J2 leaving. So it gets more complicated, but if we you could take everything that's inside and collapse it down into, say, a black body, just looking at it by itself, and then every shield that you add on after that will decrease the output by, it'll take it down to 1/2 of its original value. All right, so now if we want to know the temperature of this outer shield here, we just use Stefan Boltzmann's law, which tells us that J goes as T to the 4th power, and sigma, this Stefan Boltzmann constant, is the proportionality constant. So now we know we can just take this equation and plug this in. Basically, the sigmas are going to drop out. But we have a T2 to the 4th power equals 1/2 T1 to the 4th power. So this tells us that if we know T1 and we want to know T2, we just solve for T2 here, and we just have 1 over, this is the 4th root of 2 times T1, like that. All right, so I'll write this in a different form, why not? 2 to the negative 1/4 power times